Hello everyone, this is Giuseppe Maggiore and welcome to the Introduction to C#. This is our first proper lecture where we dive into code, and today we're going to talk about variables and expressions. In this course we're going to emphasize a lot the way the state and memory of our applications work when manipulated through the constructs of the programming language itself. I will make an attempt to always, wherever it makes sense at least, draw the state in the form of a sort of JSON format. As you know, the state, as the program is launched, is just empty. And the simplest construct in C#, which populates this state, is the declaration of variables. Variables in C# become labels in the state. Every variable has a type associated to it, so there's already a lot going on. The type defines the structure of the kind of information that we can bind to the name which the variable introduces. So the name of the variable introduces a new label which will be available in the state. The type of the variable defines the shape of the information that is allowed to be stored next to this label. And obviously, there will also be a value that we can assign to the variable, because the variable may change over time, otherwise it would be a constant. Okay, let's dive into this. The simplest variables we can define will be numbers. So we start with the type. In our case, the type will be an integer, int, and then the name of the variable, the label, age, and then, well, just a semicolon. Now, the program is now compiling. Let me add an extra empty statement here. Console write line done. I'm adding the statement here so that I can put a breakpoint and show how this all behaves when we run it. Okay, let's generate C# assets for build and debug. Playground. Yes. Now we should be able to simply run the debugger. The debugger is essentially a way to inspect the state of a program as it runs. You can see the yellow marker here on the current line where I put the red dot, the breakpoint, and on the left you can actually see the state of the program where the yellow marker for the current line has arrived. You can see that there is an age variable. You can see that the type here on the left is an integral part of the variable, and the default value is 0. And this value has been assigned to the variable. Now it's interesting to realize that there is actually a correlation between the type of the variable and the default value, because obviously the default value will have to make sense, will be a sort of safe default assumption when the variable has been declared but a value hasn't been provided yet. You can see that there is a warning here which says that the variable age has been declared. So here we have it declared, but it hasn't been used in the program, and this is a fair warning. You don't really want to have these variables declared for nothing. There are a lot of possible types. Let's take a look at a few other options. We could have strings containing text. We could have booleans containing true or false information, so just the decision of a boolean expression. Let's say lives in London. Okay, there you go. And then we have other numbers, for example, doubles and floats. Doubles are more precise than floats. They have twice as many bits, and they can represent very precise, very small numbers with a comma, and also very, very large numbers. Obviously, they do lose some precision on the insignificant digits, so doubles are not exact, just like floats, but for all practical purposes you can assume that floats will lose information and you will notice it. Double, well, it takes more work. Still, they can. And a program like this will produce the following state. Actually, we will have the age will be 0. Oh, well, let me put this behind a comment. There you go. The age will be 0. The name will be null. Lives in London will be false. And the height and the weight will be 0.0 and 0.0f respectively. Let's take a look at what the debugger has to say about this, because if all is right, the debugger will also confirm what we just said. Okay, so the age is 0, the name is null. That's interesting, by the way. Lives in London is false, height is 0, and weight is 0. Okay, very good. And you might be wondering, okay, but well, why is the name not, for example, an empty string? That would be a perfectly reasonable equivalent to the 0 or false of the other types. Well, strings are a nullable type, and nullable types can have null as a sort of representation of lack of value. So, yeah, there's that. Okay. Now, of course, just declaring values reserves space for them at their name in the space. But we also want to be able to put values inside these reserved slots of space in our state. So you could say, okay, the age is 0, the name is Giuseppe, I do not live in London, so there you go, lives in London is false, my height is 1.79, no, yeah, 1.79 meters, let's be honest, and my weight is a brisk 73.1 kilograms. Okay, notice that doubles, being the, let's say, more precise choice, they are sort of syntactically facilitated, you could say. So we can just write the type 1.79 and we don't need any extra syntax for them. Floats, the smaller types, less precise, we actually need to tag them with an F. If we remove the F, look at what happens. Well, all of a sudden, we get a compiler error saying, okay, you're trying to put a literal of type double, which is 73.1, this is a double, into a float, and you cannot really convert implicitly, so automatically, because this might lead to a loss of information. So if you really want to have a little of this type, you have to add an F. That's very helpful. Okay, so there you go. Notice that when declaring this value, oh, and of course, the state, after all these declarations with assignment, they will populate the state with the I did forget one, age is 38. There we go. We will get a state where these labels are actually connected to the value we assigned. And okay, well, I'm not going to write all of them because you get the gist of it. Let's actually run the debugger. Let's see if the debugger actually agrees with what I just stated. And the debugger seems indeed to agree. 38, Giuseppe false, 179, 73.1. Okay, very good. Now, of course, you might wonder, okay, but why would we think about the state now? The state is almost the same as the syntax of our program. Yes, that would be correct. The interesting thing about knowing how the state behaves is that when you have an application with a lot of dynamic statements, the application is running for a long time, etc., then it's a lot more interesting to be able to predict what the state is going to look like, and in your mind, what you will have will be things like, okay, x is a value between 0 and 1,000, and then there's maybe something else, y, and y will be somewhere between x divided by 2 and z times 4. So understanding of the state is not really interesting for understanding the basics of initial programs like the one we're seeing here at the beginning of our understanding of C#, but rather these complex dynamic domains which respect some rich sets of interrelations between the variables of the state. And as we introduce functions and heap, you will see that the richness of the state we can represent is much deeper because the size of the state, and so the information it represents, is actually variable itself. So that's very exciting. Now, as we discussed already, C# is a language that has evolved from the tradition of C, C++, and Java, which was a bit of an annoying tradition, in the sense that there was a lot of unnecessary detail. Compilers were still in an early stage. There was a lot of naiveness and banality to the things that we had to type every time. And in recent years, okay, recent years might be like between 20 and 15, type inference was introduced. Type inference allows us to skip the type of variable of only when there is an assignment right away, which is a very good practice anyway. So we're not really being forced to do anything that is not a very good practice anyway. And by just looking at the type of the value on the right of the equal sign, the type of the variable is inferred. So this is int, okay, int32, because by default int is a 32-bit integer. This is string. You can see it's string question mark because it means it's a nullable string. This is a boolean. This is a double, and this is a float or a single. If we remove the f now, though, well, our intention has to be guessed from, has to be inferred from the available information, and so instead of a compiler error like we got before when we declare this as float, or again, if we want to use the full name, you know, system.single, well, now we get a compiler error because the type declaration takes precedence. If we put var, yeah, then this is a valid value, even though it might not have the type that we intend. So weight is simply inferred to be a variable of type double instead of float. Var does introduce a little hazard, but it's really tiny, it's really negligible, so I strongly advise to actually use it and not think about it, when the type that's inferred might end up not being what you actually meant. But again, it's okay. Variables can change value. I could say, and this is quite a well-known process, that the age is incremented by 1. Now, as you can imagine, right before this statement, we had an age of 38, and the rest. Right after this statement, we get an age of 39. Once again, let's see this process in action. Let's put a breakpoint here. Let's start the debugger. There we are. Age is age plus 1. You can see the value is 38 here. I will now press this button which says step over, so just take one step in this source file to the next valid instruction. So we're going to jump to line 23. You see the yellow marker. It goes from line 14 to 23. And you can see that here the state has been modified. You can also see that the value that has changed is even highlighted. 38 has become 39 in the age position. Very well. And even though variables obviously, well, otherwise they wouldn't really be variables in any meaningful sense of the word, may change value, so the value that is associated with them in the state, they may not change type. So the type is fixed throughout the whole life cycle of the variable. If we make an attempt, like if we say, okay, let's say that for some surprising reason we want to be able to change the name to something else. Okay, there you go. Now we get an error that says, well, the typical error complains about the lack of an implicit conversion between the type that you're trying to assign and the type that you're trying to put this thing into. So obviously, well, what this really means is the types are not compatible, so you just cannot put it. It's you know, the very old game that we've all played when we were between 3 and 5 of a square peg in a round hole, basically. And this is the kind of the computer science transposition of that game. So this is saying square peg can't fit a round hole, but in this case it's int peg cannot fit string hole. Obviously, this being information, there are many ways to convert different types. So that's why C# is not really stating in absolute terms you cannot turn an int into a string, because that is very simply also just not true. I can turn 100 into a string, and now, bam, there you go, no compiler error anymore. And as a matter of fact, this will just work. Let me show you. Okay, next step, and you can see the name is now 100, and you can also see that, yeah, the method you called returned a string, and the string is 100, and the string has now been put into the name variable. There you go. But the conversion between 100 between an int, in this case 100, and a string cannot be done automatically. So that's what C# really means with implicit conversion. There are some conversions between types that are defined as implicit, and they just happen automatically without the programmer saying that the conversion needs to happen. And there are even conversions that are explicit. So there is a conversion, there is a special syntax for it, but you have to invoke the conversion. So it's like, okay, you can perform this conversion, but the programmer needs to state that they are aware that this conversion is about to take place. Now, variables and values, comprised of primitive types, support expressions, and expressions allow for the transformation, or even more often the combination, of multiple other values and variables. Let me give an example. Let's say we have the name and the surname, and these are two strings. We can compose the name and surname by means of the plus operator. The plus operator concatenates two strings, one after the other. Let's take a look at what the debugger has to say about this. Now, the name and the surname, we take a step, and there you go, full name now, as you can see, will be Giuseppe Maggiore, without any spaces, without anything in between. Let's improve this slightly. Well, given that the plus operator behaves in the logical arithmetic way, because strings are monoidal in nature, in case you were wondering. So basically it means you can add strings like you would add numbers, and well, you have the same properties. That, for example, you don't need to put brackets, because the order in which the sums are grouped together, the order of association doesn't really matter that much, so you can just leave it implicit, and the compiler will pick a reasonable default for us. And now, in any case, what happens is that we get a much more reasonable full name, being Giuseppe space Maggiore. Okay, excellent. There are so many expressions. One very interesting new form of expression, though, that only applies to strings, is the so-called string interpolation expression. So this is an expression that basically abstracts away the need to use the plus operator on top of different strings, and the compiler will even be able to figure out the order in which we have to perform the operations, potentially even more efficiently than by explicitly using the plus operator manually. And there you go, look at this beauty. So here what we have is a sort of template for a string. We start with $, we have the quote symbols, and then between curly brackets we can put any variables we want. We can even do more than just compose strings together. For example, we could say is age years old, and the to-string conversion, which every variable has anyway, is invoked automatically. Now, let's take a look. So, the value we get is Giuseppe Maggiore is 38 years old. Okay, makes perfect sense. Very good. In case we were interested in a particular expression, and we wanted to play with things, it's also possible to add a watch. A watch gives us an expression that we want to check, and you can put the expression, and then on the right, also notice the colon, because this is sort of suggesting, okay, it's a sort of JSON data structure anyway. After the colon, you actually see the value of this. This is actually pretty cool. We might even play a little bit with just watches now. There are plenty of arithmetic operators that are supported on all numeric types, like int and double. Let me show. We could say age times 2. Ooh, that sounds old. Age divided by 4. Okay, that sounds reasonable. 9, 18, 36. Yes, okay. Then we could say age modulus 4. So what is the remainder of the division by 4? Because 38 divided by 4 is 9, but 9 times 4 would be 18, 36. So age modulus 2 will be 2, because that is what remains of the division. If we take the height and divide it by 2, then we get 0.895. Okay, very interesting. And if we take the weight and divide by 2, we get 36.55. There are plenty of other operators or other expressions that come standard out of the box. So we have the whole math dot namespace. Let's say that math is more of a sort of module than a name. It's not really a namespace anyway. We can play with math a little bit. We could say, okay, what is math.pow of height to the power of 2, and we get, yeah, okay, 3.2. I have no idea whether or not this makes sense, but 3 to the power of 2, that will be 9. Okay, this is intuitive, very good, and so on. Let's delete all of these. Booleans also support some quite powerful operators, actually. We have, first of all, the inversion operator. Booleans can be true or false, and when we put the bang or the exclamation mark in front of it, basically the value gets flipped. So not true is false, and not false is true. Okay, this is quite easy. Sometimes, though, we have two Boolean values or two Boolean expressions, mind you, because, well, how do you introduce a Boolean? Obviously, you could say true or false, but you could say, is the age greater or equal than 18? Drinking age, there you go, or voting age. Okay, very good. But sometimes you might have richer controls and conditions that you want to apply. For example, you could say, okay, I want to know whether or not someone is either taller than 135 or older than 13 years old. So you could say age greater than 13. That's one condition. And height greater than 135. Both true. But what we want to say, we want both of these conditions to be true at the same time. Then we use the double ampersand operator. Double ampersand operator takes two values and says true only if both of them are true. In any other case, it will say false. This is the conjunction or AND operator. It's the logical AND. It corresponds roughly to multiplication. So if you see true as 1 and false as 0, the AND operator roughly corresponds to the product of the two values when interpreted as 0 and 1. We could have also written the previous operation as follows: age greater than 13 and height greater than 1.35, and the result is true. Notice that we don't need to put any brackets. This is by design. Comparison operators like greater than, smaller than, greater equal, etc. have a higher precedence than Boolean manipulation operators. Why is that? Well, the reason is actually precisely not to have to put brackets around this kind of expression, because usually you introduce a Boolean in your program by a comparison, greater than, equal, not equal, etc. And then you might combine this with other conditional expressions. So even though the relationship between these two domains, the domain of comparison operators and booleans, is somewhat arbitrary from an operator precedence perspective, from a usability and developer experience perspective, this ends up being the most streamlined and comfortable choice. There are many comparison operators. For example, you could say, is the age equal to 12? Answer is false. If we check if the age equal to 38, then this is true, of course. Is the age different than 18? So bang exclamation mark equal, bang equal is the not equal sign, and well, this is true because 38 is not equal to 18, and so on. All right. There are a lot more symbol types that we don't really cover explicitly. There are single characters, so we could say that A is a single character. Notice that we cannot put the double quotes because, well, in this case it's probably going to complain that there is no implicit conversion from string to char, and this makes perfect sense, by the way, because a string contains strictly more information, way too many bits for a character. We cannot put multiple characters in a char because, well, it makes sense, it's just one, so it can only be just one single little Unicode character. We have bigger data types, so we have, for example, longs, which are long integers. Let me see, I think, yes, it's U, meaning that, well, oh, uint, wait, is this just L? Yes, is it L though? Oh, that's a friendly error. The L suffix is easily confused with the digit 1. Use capital L. Okay, so when we want to store very big values, the maximum integer is relatively speaking small, but if we're dealing with mathematical applications like dealing with well, currencies, no, you have to be really rich to have any issue with this. But for example, if you're dealing with scientific domains, if you're, I don't know, counting scientific quantities, molecules, or this kind of thing, then long values will be a lot more suitable than integers, even though they will be a bit slower and they will eat up more memory. Let me see what the expression is. Int32 dot max value, yes. Let's also compare these. So let's put a max value as one of the watches, and let's also get an int 64, which is long, and let's see the max value of this. And I've also seen something I haven't ever used in practice, an int 128. You know, I started programming a lot of many years ago, so for me these things were even int 64s, even longs were sort of a forbidden fruit when we had 64 megabytes of RAM total. Okay, you can see that in 32 that's actually 2 billion, and 2 billion is not a lot. It's small. Like if you need just a counter of the values in your array, there's no way your array contains more than 2 billion values, because probably, okay, it could happen, but probably there is not much you can do with such an array. If it contains complex data structures, you will run out of memory anyway, and iterating 2 billion values takes a lot of time, etc. So for just counters and the sort of internal program management task, int32, regular plain old int, is great. int64, yeah, I have no idea what this is. This is just a huge number. You can see how big of a number it is. And int 128, this is kind of this is in the insane domain. Obviously, computers are very good at manipulating values, large values, so if you need very big values, well, the computer is still going to be crazy fast, but I suspect max value is probably Yeah, this is probably a more complicated class, so this is something custom. So int32 and int64 are certainly supported by any hardware. So your CPU has specialized instructions for the manipulation of these values at, well, basically one cycle of your CPU clock. This is very important because you know that your CPU can run between usually between 1 and 4 gigahertz. These are reasonable numbers between laptops and desktops, meaning that there is one CPU clock cycle for well, one gigahertz would be there's one so okay, kilohertz, megahertz, gigahertz, so 1 billion CPU clock cycles per second. That's a lot. And these specialized hardware instructions, like adding two integers, they take just one of those little slots, meaning a lot. Something like int 128, well, I don't think every CPU, I don't know how many commercial CPUs even have support for the 128-bit arithmetics in one clock operation. So all of a sudden you might have operations that take 10, 100 CPU clock cycles, etc. So all of a sudden you slow down to a crawl in the execution and evaluation of expressions around this. Other data types you might encounter are the ones which shorthand name begins with U. So for example, U long stands for unsigned long. You can see that we have the same variations. U int 16, it's even smaller than 32. U int 32, etc. These are numbers that do not have a sign, so they are only positive. Let me show one small difference. System.uint32.max value, and let's run the debugger now. Let's see what happens. Well, this is 4 billion, because obviously when you're dealing with signed values, well, half of the values, or half minus 1, will be to the left, so will be negative to the left of 0, and then the other half will be positive values. And if you're unsigned, but you use the same number of bytes, obviously you're able to represent all the values after the 0, so you have twice as many values that you can represent. Okay, let me think. System.decimal, yes. Decimals are also an interesting data type. I want to at least mention these things. If you need to use them, then Google at some point will be your best friend. But decimals are the most precise floating point values. Height and weight, in this case, they are doubles and floats. And doubles and floats, they do their best, but you might encounter precision issues. And those precision issues can be very nasty because they tend to compound. So you will just get errors, and these errors do happen, and it's a nightmare when dealing with this kind of types. Decimals do not have this problem. Decimals are infinitely precise floating point values. They are represented basically as fractions. This comes at a price, namely decimals are a lot slower than doubles and floats, because doubles and floats, very much like longs and ints, are CPU supported. So these operations take one CPU clock cycle and nothing more. So they're super fast. Decimals, on the other hand, well, they do require some mathematical operations, and well, those will most likely not be supported directly in one single clock tick of the CPU. And so, yeah, you gain precision, you lose performance. All right. Now, my advice at this point would be do take a look at the documentation, take a look at how many data types are available, start playing with it, start setting up your projects, and well, that's enough for the first lecture. I wish you the absolute best in this beautiful journey of learning. C# is a powerful, pragmatic, and exceedingly powerful and versatile language. We're going to have a lot of fun together, and see you next time. Bye bye.